Metal weatherheads are commonly used on polyvinyl chloride, or PVC, service risers to protect the electrical wires and connections from moisture and weather conditions. The bonding requirements for metal weatherheads on PVC service risers can vary depending on local electrical codes and regulations. In many areas, bonding is required to ensure safety and prevent electrical shock. If bonding is required, the following types of connections are commonly used. Firstly, direct connection. The metal weatherhead is directly connected to the PVC service riser using a bonding clamp or other approved method. Secondly, a grounding wire. A grounding wire is run from the metal weatherhead to a grounding rod or other approved grounding electrode. Bonding the metal weatherhead provides several benefits. Firstly, electrical safety. Bonding helps prevent electrical shock by creating a low resistance path to the ground, diverting any fault currents. Secondly, compliance with code. Bonding meets the requirements of most electrical codes, ensuring compliance with safety standards. Thirdly, protection against lightning. Bonding provides a path for lightning to travel safely to the ground. Generally, bonding is required in areas where the following conditions exist. Firstly, high moisture, meaning areas with excessive rainfall or humidity. Secondly, electrical circuits, where the electrical circuit requires a ground path for safety. Thirdly, lightning-prone areas to protect against lightning strikes. Some local electrical codes may have specific bonding requirements for metal weatherheads. It is crucial to consult with a local electrical inspector or qualified electrician to determine the specific bonding requirements in your area. Failure to properly bond the metal weatherhead can pose a safety hazard and void the warranty of the electrical equipment. Electrical bonding is a critical aspect of electrical safety, serving to connect conductive parts of an electrical system to create a low impedance path for fault current. This path facilitates the operation of overcurrent protective devices, such as circuit breakers or fuses, which interrupt the circuit in the event of a fault, thereby minimizing the risk of electrical shock and fire hazards. The principles of electrical bonding are rooted in Ohm's law and Kirchhoff's laws, which govern the behavior of electrical circuits. According to Ohm's law, the current flowing through a conductor is directly proportional to the voltage and inversely proportional to the resistance. Kirchhoff's laws state that the sum of currents entering a node equals the sum of currents leaving the node, and the sum of the voltages around any closed loop in a circuit is zero. Effective electrical bonding ensures that all metal parts of an electrical system are at the same electrical potential. This equipotentiality prevents voltage differences that could cause current to flow through unintended paths, such as a person touching two metal parts with different potentials. The National Electrical Code, or NEC, provides detailed requirements for electrical bonding to ensure the safety of electrical installations. The NEC is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. Its provisions are designed to protect people and property from electrical hazards. Article 250 of the NEC specifically addresses grounding and bonding requirements. It outlines the methods and materials required to establish an effective ground fault current path. This path is essential for the proper operation of overcurrent protective devices. Key components of an electrical bonding system include bonding jumpers, grounding electrode conductors, and equipment grounding conductors. Bonding jumpers are used to connect metal parts of an electrical system to ensure electrical continuity. Grounding electrode conductors connect the electrical system to a grounding electrode, such as a ground rod or a metal water pipe. Equipment grounding conductors provide a path for fault current to flow back to the source, allowing overcurrent protective devices to operate. The size of bonding conductors is determined by the size of the overcurrent protective device protecting the circuit. Table 250.102. C1 of the NEC provides guidance on the minimum size of bonding jumpers based on the rating of the overcurrent protective device. For example, if a circuit is protected by a 20 amp circuit breaker, the minimum size of the bonding jumper would typically be 12 American wire gauge, or copper. Grounding electrodes must meet specific requirements outlined in the NEC. Ground rods must be at least 8 feet long and driven into the ground. Metal water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. The resistance of the grounding electrode system should not exceed 25 ohms. If the resistance exceeds 25 ohms, an additional grounding electrode is required. Electrical bonding is particularly important in hazardous locations, such as areas where flammable gases or vapors are present. In these locations, bonding is essential to prevent the accumulation of static electricity which could ignite the flammable atmosphere. The NEC provides specific requirements for bonding in hazardous locations in Article 500 through Article 516. These requirements include the use of intrinsically safe equipment and the installation of additional bonding jumpers to minimize the risk of static discharge. Regular inspection and testing of electrical bonding systems are crucial to ensure their effectiveness. Bonding connections should be checked for tightness and corrosion. The resistance of the grounding electrode system should be measured to verify that it meets the NEC requirements. Any deficiencies should be corrected promptly to maintain the safety of the electrical installation. The use of improper bonding techniques can create significant electrical hazards. For example, using undersized bonding conductors can limit the flow of fault current, preventing overcurrent protective devices from operating properly. This can result in prolonged exposure to fault current, increasing the risk of electrical shock and fire. Another common mistake is failing to bond all metal parts of an electrical system. This can create voltage differences between metal parts, leading to the flow of current through unintended paths. This can damage equipment and create a shock hazard. Electrical bonding also plays a crucial role in protecting electronic equipment from damage due to voltage surges and electromagnetic interference, or EMI. Proper bonding provides a low impedance path for surge currents to flow to ground, diverting them away from sensitive electronic components. Bonding also helps to reduce EMI by minimizing the size of ground loops, which can act as antennas, radiating or receiving unwanted signals. The NEC requires the bonding of metal enclosures for electronic equipment to ensure effective surge protection and EMI reduction. Article 640 of the NEC provides specific requirements for the grounding and bonding of audio, video, and similar electronic equipment. In addition to the NEC, other standards such as the Institute of Electrical and Electronics Engineers, or IEE, Standard 142, also known as the Green Book, provide guidance on electrical grounding and bonding practices. The Green Book offers detailed recommendations for the design and installation of effective grounding systems for industrial and commercial power systems. It covers topics such as grounding electrode systems, bonding techniques, and surge protection. The effectiveness of an electrical bonding system depends on the quality of the materials and workmanship used in its installation. Bonding conductors should be made of corrosion-resistant materials such as copper or aluminum. Bonding connections should be made using approved connectors and techniques. The surfaces of metal parts should be cleaned and prepared before making bonding connections to ensure good electrical contact. Training and certification are essential for electricians and other electrical workers who install and maintain electrical bonding systems. Proper training ensures that electrical workers understand the principles of electrical bonding and are familiar with the NEC requirements. Certification demonstrates that an electrical worker has the knowledge and skills necessary to perform electrical work safely and effectively. The National Fire Protection Association, or NFPA, offers several certifications for electrical workers, including the Certified Electrical Safety Worker, or CESWR, certification. The CESWR certification demonstrates competency in electrical safety practices, including grounding and bonding. In summary, electrical bonding is a critical aspect of electrical safety that helps to prevent electrical shock, fire hazards, and equipment damage. The NEC provides detailed requirements for electrical bonding to ensure the safety of electrical installations. Proper bonding techniques, materials, and workmanship are essential for an effective bonding system. Regular inspection and testing of bonding systems are crucial to maintain their effectiveness. Training and certification are essential for electrical workers who install and maintain electrical bonding systems. By following these guidelines, electrical professionals can ensure the safety and reliability of electrical systems. Now let's delve into the specifics of bonding metal weatherheads on PVC service risers, considering the interplay of different materials and environmental factors. Firstly, understanding the materials involved is paramount. Metal weatherheads are typically constructed from aluminum or galvanized steel, chosen for their durability and resistance to weather elements. PVC, or polyvinyl chloride, on the other hand, is a plastic polymer known for its insulating properties and resistance to corrosion. The junction between these dissimilar materials presents unique challenges for electrical bonding. The primary purpose of bonding a metal weatherhead to a grounding system is to create a low impedance path for fault currents. This path ensures that in the event of a fault, such as a lightning strike or a short circuit, the current will safely flow to ground, tripping the circuit breaker and preventing electrical shock or fire. The NEC mandates bonding to specific standards, and local codes often add further layers of requirements, reflecting regional environmental conditions and electrical infrastructure. When a metal weatherhead is installed on a PVC service riser, the PVC itself acts as an insulator, interrupting the electrical continuity between the weatherhead and the grounding system. Therefore, a separate bonding conductor must be installed to bridge this gap. The most common method involves attaching a bonding clamp to the metal weatherhead and running a grounding wire to the service grounding electrode system, which typically includes a ground rod or a connection to the metal water pipe entering the building. The size of the bonding conductor is crucial and must be selected based on the size of the service conductors, as specified in NEC Table 250.102. C1. Using an undersized conductor can limit the fault current capacity, potentially delaying the tripping of the circuit breaker and increasing the risk of electrical hazard. Furthermore, the bonding conductor must be protective from physical damage. This can be achieved by running the conductor inside a conduit or securing it to the PVC riser with appropriate straps. The connections at both ends of the bonding conductor must be made with corrosion-resistant connectors listed for the purpose. Oxidation and corrosion can increase the resistance of the connection, compromising its effectiveness. In areas with high moisture or corrosive environments, additional protection, such as the application of antioxidant compounds, may be necessary. Grounding electrodes themselves must meet stringent requirements. A ground rod, typically made of copper-clad steel, must be at least 8 feet long and driven into the ground until at least 8 feet of contact with the soil. The NEC also permits the use of the metal water pipe as a grounding electrode, but this connection must be supplemented with an additional grounding electrode, such as a ground rod, to ensure redundancy. The resistance of the grounding electrode system should not exceed 25 ohms. This resistance can be measured using a ground resistance tester, and if it exceeds the limit, additional ground rods may need to be installed to reduce the resistance. Lightning protection is another critical consideration, especially in areas prone to thunderstorms. A properly bonded metal weatherhead can provide a path for lightning current to flow to ground, protecting the electrical system from damage. However, a comprehensive lightning protection system typically includes additional components such as lightning rods and surge protective devices, or SPDs, to provide comprehensive protection. SPD are installed at the service entrance and as sensitive electronic equipment to divert surge currents away from the equipment. The NEC provides specific requirements for lightning protection systems in Article 280 and Article 285. Local electrical inspectors play a vital role in ensuring compliance with bonding requirements. They review electrical plans, inspect installations, and enforce the NEC and local codes. Consulting with a local electrical inspector before starting an electrical project can help to avoid costly mistakes and ensure that the installation meets all applicable requirements. Documenting the bonding system is also essential for future maintenance and inspections. This documentation should include a diagram showing the location of all bonding conductors, grounding electrodes, and connections, as well as the size and type of materials used. Regular inspections of the bonding system should be conducted to check for corrosion, loose connections, and physical damage. Any deficiencies should be corrected promptly to maintain the effectiveness of the system. In addition to the NEC and local codes, other standards and guidelines, such as those published by the IEE, provide valuable information on electrical grounding and bonding practices. These resources can help electrical professionals to stay up to date on the latest technologies and best practices. In conclusion, bonding metal weatherheads on PVC service risers is a critical aspect of electrical safety. It requires careful consideration of materials, environmental factors, and applicable codes and standards. By following the guidelines outlined in the NEC and consulting with local electrical inspectors, electrical professionals can ensure that these installations are safe, reliable, and compliant. Let's expand on specific scenarios and address frequently asked questions related to bonding metal weatherheads on PVC service risers. Imagine a coastal environment where the air is laden with salt. Salt water is a highly corrosive electrolyte, accelerating the degradation of metal components and connections. In such environments, the selection of corrosion-resistant materials is paramount. Stainless steel or copper connectors and bonding conductors are preferred over galvanized steel. Furthermore, applying a corrosion-inhibiting compound to all connections can significantly extend their lifespan. Regular inspections, perhaps annually, are crucial to identify and address any signs of corrosion before they compromise the integrity of the bonding system. Consider another scenario where the service riser is located near a swimming pool or other water feature. The NEC has specific requirements for bonding metal parts near swimming pools to create an equipotential bonding grid. This grid minimizes voltage gradients in the pool area, reducing the risk of electric shock to swimmers. The metal weatherhead must be integrated into this equipotential bonding grid, ensuring that it is at the same electrical potential as other metal parts, such as the pool reinforcing steel, metal ladders, and underwater lighting fixtures. Now let's address some frequently asked questions. One common question is whether it is permissible to use the neutral conductor as a grounding conductor for bonding the metal weatherhead. The answer is generally no. The NEC prohibits using the neutral conductor as a grounding conductor on the load side of the service disconnecting means. The grounding conductor must be a separate conductor that is connected to the grounding electrode system. Another frequent question pertains to the use of aluminum conductors for bonding. Aluminum conductors are permitted for bonding, but they must be properly sized and installed to account for their higher resistance and potential for corrosion. Aluminum conductors must be terminated with connectors that are listed for use with aluminum, and an antioxidant compound should be applied to the connections to prevent corrosion. Another important consideration is the impact of surge protective devices, or SPDs, on the bonding system. SPD are designed to divert surge currents to ground, protecting electronic equipment from damage. However, SPD can also create transient voltage differences between different parts of the grounding system. To minimize these voltage differences, it is essential to install SPD with short, low-impedance grounding conductors. The grounding conductor should be connected to a common grounding point to minimize the impedance between the SPD and the grounding electrode system. The NEC provides specific requirements for the installation of SPD in Article 285. Furthermore, consider the case of older homes where the electrical system may not be up to current standards. In these situations, it is often necessary to upgrade the grounding system to meet the requirements of the NEC. This may involve installing new grounding electrodes, replacing undersized grounding conductors, and adding additional bonding connections. It is essential to consult with a qualified electrician to assess the existing electrical system and develop a plan for upgrading it to meet current standards. Now, let's address the situation where the metal weatherhead is painted or coated. Paint and coatings can act as insulators, preventing good electrical contact. Before making a bonding connection, the paint or coating must be removed from the metal surface to ensure a low impedance connection. The area where the paint is removed should be large enough to accommodate the bonding connector. After the connection is made, the bare metal should be protected with a corrosion-inhibiting compound to prevent rust and corrosion. Another important aspect is the coordination between the bonding system and the communications grounding system. Communications equipment, such as telephone and data lines, also require grounding to protect against surge currents and electrical noise. The communications grounding system should be bonded to the electrical grounding system to create a common grounding reference. This bonding helps to minimize voltage differences between the two systems and reduces the risk of damage to communications equipment. The NEC provides specific requirements for the bonding of communications grounding systems in Article 800. In summary, bonding metal weatherheads on PVC service risers requires a thorough understanding of materials, environmental factors, and applicable codes and standards. By considering these factors and following the guidelines outlined in the NEC, electrical professionals can ensure that these installations are safe, reliable, and compliant. The importance of proper bonding cannot be overstated, as it is a critical component of electrical safety. Remember to always consult with a qualified electrician and the local electrical inspector to ensure that all bonding requirements are met. Let's now consider specific tools and techniques utilized in the process of bonding metal weatherheads, emphasizing precision and adherence to safety protocols. One essential tool is a reliable multimeter, which is used to verify the continuity of the bonding connections and measure the resistance of the grounding electrode system. A multimeter should have a low resistance measurement range to accurately measure the impedance of the bonding connections. The meter should also be calibrated regularly to ensure accurate readings. Another crucial tool is a bonding clamp, which is used to securely attach the bonding conductor to the metal weatherhead. Bonding clamps must be listed for the specific type of metal being used, whether it is aluminum or steel. The clamp should be sized appropriately for the conductor and should provide a tight, corrosion-resistant connection. A wire stripper is used to remove the insulation from the bonding conductor without damaging the conductor itself. Wire strippers should be selected based on the size of the conductor being used. It is important to use the correct size stripper to avoid nicking or cutting the conductor, which can reduce its current carrying capacity. A crimping tool is used to attach connectors to the bonding conductor. Crimping tools must be listed for the specific type of connector being used. The crimping tool should be calibrated regularly to ensure that it provides a tight, reliable connection. A torque wrench is used to tighten bonding connections to the manufacturer's specified torque. Using a torque wrench ensures that the connection is tight enough to provide good electrical contact, but not so tight that it damages the connector or the metal weatherhead. A ground resistance tester is used to measure the resistance of the grounding electrode system. Ground resistance testers use a 3-point method to measure the resistance of the grounding electrode. The tester sends a current through the grounding electrode and measures the voltage drop to determine the resistance. Safety equipment is also essential when working with electrical systems. This includes insulated gloves, safety glasses, and appropriate work clothing. Insulated gloves protect against electric shock. Safety glasses protect the eyes from flying debris. Appropriate work clothing, such as long sleeves and pants, protects the skin from burns and other injuries. Before beginning any electrical work, it is essential to de-energize the circuit and verify that it is de-energized using a multimeter. Lockout-tagout procedures should be followed to prevent accidental re-energization of the circuit. Lockout-tagout involves placing a lock and a tag on the circuit breaker to indicate that the circuit is being worked on. The tag should include the name of the person who is working on the circuit and a warning not to re-energize the circuit. When making bonding connections, it is important to clean the metal surfaces to remove any dirt, grease, or corrosion. A wire brush or emery cloth can be used to clean the metal surfaces. After the surfaces are cleaned, a corrosion-inhibiting compound should be applied to prevent rust and corrosion. When running the bonding conductor, it is important to avoid sharp bends or kinks in the conductor. Sharp bends can reduce the current carrying capacity of the conductor and can also make it more difficult to pull the conductor through conduit. The bonding conductor should be supported at regular intervals to prevent it from sagging or coming into contact with other objects. When terminating the bonding conductor, it is important to use the correct type of connector for the application. Connectors should be listed for the specific type of metal being used and should be sized appropriately for the conductor. The connector should be installed according to the manufacturer's instructions. After the bonding connection is made, it is important to verify the continuity of the connection using a multimeter. The resistance of the connection should be very low, typically less than 0.1 ohms. If the resistance is higher than expected, the connection should be inspected and tightened. Regular inspections of the bonding system should be conducted to check for corrosion, loose connections, and physical damage. Any deficiencies should be corrected promptly to maintain the effectiveness of the system. By following these tools and techniques, electrical professionals can ensure that bonding metal weatherheads on PVC service risers is performed safely and effectively. Now, let's shift our focus to the inspection and maintenance aspects of bonded metal weatherheads on PVC service risers, ensuring long-term reliability and safety. Regular inspections are paramount to identify potential issues before they escalate into hazardous conditions. These inspections should be conducted at least annually and more frequently in harsh environments such as coastal areas or industrial settings. A visual inspection should begin by examining the metal weatherhead for signs of corrosion, rust, or physical damage. Pay close attention to the seams, joints, and mounting points. Any evidence of corrosion should be addressed promptly by cleaning the affected area and applying a corrosion-inhibiting compound. If the weatherhead is severely corroded, it may need to be replaced. Next, inspect the bonding conductor for any signs of damage, such as cuts, abrasions, or kinks. Ensure that the conductor is securely fastened to the weatherhead and the grounding electrode system. Check the connections for tightness and corrosion. Loose connections can increase the resistance of the bonding path, reducing its effectiveness. Corroded connections can also increase resistance and can eventually lead to a complete loss of continuity. Use a torque wrench to tighten the connections to the manufacturer's specified torque. If corrosion is present, clean the connections with a wire brush and apply a corrosion-inhibiting compound before tightening. The grounding electrode system should also be inspected to ensure that it is in good condition. Check the ground rods for corrosion or damage. Ensure that the connections to the ground rods are tight and corrosion-free. If the grounding electrode system includes a metal water pipe, inspect the pipe for corrosion and ensure that it is properly bonded to the electrical system. Measure the resistance of the grounding electrode system using a ground resistance tester. The resistance should be less than 25 ohms. If the resistance is higher than 25 ohms, additional ground rods may need to be installed to reduce the resistance. Documentation is an essential part of the inspection and maintenance process. Keep a record of all inspections, maintenance activities, and test results. This record should include the date of the inspection, the name of the inspector, a description of any problems found, and the corrective actions taken. The documentation should be kept in a safe place and should be readily available for review. In addition to regular inspections, periodic maintenance is also necessary to ensure the long-term reliability of the bonding system. This maintenance may include cleaning the weatherhead, tightening connections, replacing corroded components, and testing the grounding electrode system. The frequency of maintenance will depend on the environmental conditions and the severity of any problems found during inspections. When performing maintenance, always de-energize the circuit and follow lockout-tagout procedures to prevent accidental re-energization. Use appropriate safety equipment, such as insulated gloves and safety glasses. After completing the maintenance, verify the continuity of the bonding connections and measure the resistance of the grounding electrode system to ensure that the system is functioning properly. If any problems are found, correct them before re-energizing the circuit. In summary, inspection and maintenance are essential for ensuring the long-term reliability and safety of bonded metal weatherheads on PVC service risers. Regular inspections, periodic maintenance, and proper documentation are all critical components of an effective maintenance program. By following these guidelines, electrical professionals can help to prevent electrical hazards and ensure that electrical systems are functioning safely and reliably.